Hey y'all, we are Memphis Kim University and we are back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today we're going to be continuing our basic derivative topics unit. We are going to be doing absolute value and limits and derivatives. So absolute value is actually a pretty tricky concept. A lot of students have trouble with it. They don't know how to deal with those bars. So what we're going to do today is we're going to talk about how to view absolute value as its piecewise form. Try to think of it not as this V, but really this line and this line sort of combined. And when you think about absolute value not as a whole, but either of the two lines, then it'll be easier to apply absolute value to derivatives and limits. So let's see how this works. So again, what we're going to try to do is absolute value of limits and derivatives. Limits and derivatives. So everybody knows what absolute value looks like since algebra 1. It's that famous looking V. So let's draw that real quick. V and V. So the problem with absolute value is that it's not just one function, it's sort of two functions. It's a piecewise function. There's this line and this line. So let's define it as a piecewise function. F of x equals this. So remember that this line of absolute value is the best line. It's just the identity line on the positive side of the x-axis. So it's x for all x greater than 0. And then on the negative side, it's just the negative identity line, minus x for x smaller than 0. So again, as we do these questions, this is what absolute value is. We can write absolute value on the bottom here. As we do these questions, we're not going to try to think about absolute value as a whole. What we're going to do is we're going to determine which piece that we're talking about in each question. So we're not going to be working with both pieces, or even if we're working with both pieces, we're going to split it up and work it with both pieces separately. So I'm going to work with the negative side, and then I'm going to work with the positive side. And what's happened is, again, our goal is to get rid of these pesky absolute value bars. And how we're going to do it is we're going to determine what piece we're working with. If we're working with a positive piece, then all we have to do is erase the absolute value bars. Because absolute values on positive quantities doesn't do anything. Like the absolute value of 7 is 7. The absolute value bars could have just not been there. For the negative piece, it's a little bit trickier, but all we're going to do is change the absolute value bars to a parentheses, and then we're going to negate the quantity. Because what does absolute value do to negative quantities? It's negative that negative quantity, and then you'll get a positive quantity. So for example, the absolute value of negative 7 is again negative 7, which is 7. So again, what we're going to try to do is we're going to try to determine what piece we are on, and that's going to be by plugging in a number, determining whether we have a positive thing or a negative thing. And after we do that, if it's positive, that's great. We'll just erase those absolute value bars. If it's negative, that's still fine. We'll erase the absolute value bars and then put a negative instead. So let's see that in action. So let's start off with some more basic examples, and then we'll get harder as the video goes on, just like normal. So in this case, what I'm going to do is I'm going to do the limit as x goes to 2 minus of the function x minus 2. So we're just going to do this simple limit right here just to practice a little bit with this idea. So I look at this question and I'm like, oh my gosh, there's absolute value. I'm so intimidated. But I remember that I want to get rid of absolute value bars, and once I do, the question becomes a little bit easier. So what I'm going to do is I'm going to not look at the absolute value bars, but I'm only going to consider the quantity in the absolute value bars. So in this case, it's x minus 2. And what I'm going to do is I'm going to plug in an appropriate number so I can see if the limit that I care about, whether that's going to be a positive quantity or a negative quantity. So remember that 2 minus means that I'm approaching 2 from the left. So I'm going to plug in a number like 1.9 because we're approaching 2 from the left. Here's 2, 1.1, here's 1, 1, 1.5, 1.9, 1.9, 1.99, 1.999999. So those are the numbers we're going to have. So let's say we plug in 1.9 here for x. And again, I don't actually plug it into the absolute values. I just evaluate this quantity. So 1.9 minus 2 is equal to, I actually don't care what it's equal to. I just want to see if it's negative or not. So in this case, 1.9 minus 2 is negative. So how do we get rid of these absolute value bars? Well, because we have a negative quantity, what we're going to do is we are going to change the absolute value bars to parentheses, because I want to get rid of them. So in this case, I've changed the absolute value bars to parentheses, x minus 2. And then what I do is I negate this thing. So that's how I get rid of the absolute value bars. Again, I plug in an appropriate number. In this case, a number a little bit left of 2. When I plug that number into the quantity of the absolute value bars, I got a negative number, and a negative number means to get rid of the absolute value bars, because what is absolute value on the negative side of absolute value? It's just the negative of whatever you have in the absolute value bars. So once you got rid of the absolute value bars, then the question becomes pretty easy. Notice all I have to do is just plug in 2. When you plug in 2, you'll get negative 0, which is 0. So this is this limit right here. So again, always the goal is to get rid of absolute value bars, and it's not that bad. Just determine which side are you on. Are you on the positive side or are you on the negative side? Keep in mind, it's not based off left limit or right limit. You actually want to plug in a number. If you get a positive quantity, that's great. The absolute value bars just go away. If you get a negative number, that's fine as well. Just change your absolute value bars to parentheses, just like we did for this one, and then a gate. So let's try a little bit of a harder example, or maybe just the next example. Not much harder than this one. So the next one I'm going to do is the limit as x goes to 4 from the right, and then we're going to have 2x minus 8 on the top and absolute value bars, and then we're going to have x minus 4 on the bottom. So here I see this limit. So what am I going to do? Well, first off, I see absolute value bars, and my instinct tells me the absolute value bars is the enemy. I need to get rid of them as quickly as possible. Once I do get rid of them, I might be able to do the question. So how do you get rid of absolute value bars? Well, what you do is you determine which side of the absolute value bar are we on. So it's a famous V. Are we on this side of the absolute value bars, or are we on this side of the absolute value bars? So what you do is you plug in an appropriate number. In this case, we're approaching 4 from the right. So here's 4, and we're approaching it from the right. So we're going to be plugging in numbers like 4.1. So I do 2 times 4.1 minus 8. And what I do is I just consider what the number is. I don't actually care about what this number is. All I care about is its sign. So 2 times 4.1, well, that's going to be bigger than 8. So when I subtract 8, that's going to be a positive number. And so I get the good sort of scenario. Anytime you plug in your appropriate number and you get a positive thing for the quantity inside the absolute value bars, that means the absolute value bars aren't really doing anything in this question. Because again, absolute value on positive quantities, the absolute value is really doing nothing, because the absolute value of 7 is 7. So in this case, it's going to be very easy. All you have to do is you just have to erase the absolute value bars. So it's going to be 2x minus 8. Because again, this is a positive quantity. It's not based off the right. It's because we got a positive quantity when we plugged in an appropriate number. On the bottom here, it didn't have any absolute value, so this remains x minus 4. So now, all we have to do this limit right here. There's various ways to do this limit, but notice it's so much easier because we got rid of the absolute value bars and we did it correctly. So now we can just focus on this limit. I think of 2 different ways you can do it. The first way, which is probably the slightly harder way, is to plug in 4 here. Notice that you get 0 over 0, and then you lope that call, or you apply L'Hopital's rule. So you'll take the derivative of the top and the derivative of the bottom. That'll just be 2 over 1. Another way is to recognize, well, I can factor out a 2. Limit as x goes to 4 plus. And we're going to factor out a 2. And notice that I can just cancel out these x minus 4s quite nicely. Boom, boom. And then the answer is 2. So again, these limit absolute value questions aren't the worst thing in the world if you can deal with the absolute value bars immediately, so that you just change the question to a question that doesn't have absolute value bars. And usually that second question without absolute value bars is a lot easier of a limit than our previous limits, because you usually don't have to apply chain rule with L'Hopital's, or do multiple L'Hopital's rule, or do definition of derivative, or anything like that. Usually it's a pretty simple limit. The meat of the question, the essence of the question, is just what to do with the absolute value bars. So once you're done with that, then the question becomes easier. And again, always the goal when you see absolute value bars, it's just try to get rid of them in the appropriate manner. So let's do a little bit of a harder question, something that involves both sides. So let's say we have limit as x goes to 6, and then we're going to go, let's say on the top here we are going to have 18 minus 3x, and then on the bottom here we're going to have x minus 6. Before we do this, let's do another question in the meantime. Let's do the same exact question, but instead, let's go to x to the negative 6. So remember that one limit strategy that you can always do is just literally plugging the number into this question. If you get a number, you're actually just good to go. If you get 0 over 0, then you might have to do something if you get an indeterminate form. So in my opinion, this question is actually pretty easy. I have absolute value bars. I can try to think about trying to get rid of them. But notice when I plug in -6, I'm just going to get a number here. Because when I plug in -6, on the bottom here, it looks like it's going to be -6 minus 6. On the top, it's going to be 18 minus 3 times -6. So that looks like it's going to be, on the top here, absolute value of 18 plus 18, because it's -3 times -6 over -12. And I think I just get 36 over -12, which is -3. So notice that in this question, I just got an answer, and I don't have to get rid of the absolute value bars because they weren't really a nuisance in this case. I plugged in my -6, just like I normally apply limits, and I got a number, and I was done. What's the problem with this guy right here? Why can't we do the same thing? Well, when we plug in 6, unfortunately we get something weird. We're going to get 0 over 0. And usually when I get 0 over 0, what happens is I like to apply L'Hopital's rule. I like to take the derivative of the top and then the derivative of the bottom. But in this case, I'm not going to be able to take the derivative of the absolute value of 18 minus 3x. I don't know how derivatives work with absolute value until later on in the video. So I need to do something else. So this question on the left is a lot harder because we got 0 over 0. Basically, we are going to the worst number possible, which is 6. And then this one on the right was actually pretty easy because we could just plug in -6 and we didn't get an indeterminate form. So let's focus on this guy because this is the guy you're most likely to see. You're not as likely to see this limit right here. So I'm going to erase this. So again, we got 0 over 0. So what I need to do is I need to work with this limit a little bit algebraically. And our first two questions, what we did is we had a limit as x goes to 2 from the left, and then we had a question as limit as x goes to 4 from the right. So what we have to do here is we have to find both of those limits in the context of this question. We're going to find limit as x goes to 6 from the left, and then limit as x goes to 6 from the right. And then what will happen is that we will try to compare the numbers. If they are equal, that means that this limit is going to be equal, and if they're not equal, that means that the limit won't exist. Remember that anytime you're doing a limit, you can find the two one-sided limits, and if they're equal, that's what the answer is. And this is the main case that you do need to find two one-sided limits because absolute value is a little bit weird. Again, it's this v, so it's two different functions. So that's why we're trying to do two different limits. So let's just leave this question aside, and let's try to find the two one-sided limits. So limit as x goes to 6 from the left. Hopefully you can tell my differences between my ones and absolute values, but this is absolute value of 18 minus 3x. And then we have this here, 6 plus, and then we have x minus 6, 18 minus 3x. So we're gonna find, again, these two one-sided limits separately. So we're gonna do two separate questions. What we wanna do is we, again, wanna try to get rid of the absolute values in each of these cases. Let's actually do this one right here. So what we do is we plug in a number really, really close to 6 on the appropriate side. In this case, we're going from the left. So a good number to plug in would be, for example, 5.9. So we have 18 minus 3 times 5.9. I don't actually care about what this number is. All I'm trying to determine is whether this is positive. And this one actually is positive. So we're gonna write positive here. And because this is positive, that means that in order to get rid of the absolute value bars, well, because we have a positive quantity, absolute value does nothing to the positive quantity, so we can just erase the absolute value bars. So you have limit as x goes to 6 minus 18 minus 3x. We can just erase the absolute value bars over x minus 6. Let's finish this question immediately because we do have the no absolute value bars, and that's just lovely. So all I'm going to do is I'm going to cancel this out. Notice that this thing, if you want, you can write it as -3 times x minus 6, just to make things a little bit easier to cancel. You cancel these guys, or you could have applied L'Hopital's rule. This answer is going to be -6 for this side of the limit. So now we're going to do the same thing with 6 plus. All we're trying to do is try to get rid of the absolute value bars, and that entails, do we write a positive in front of it, or do we write a negative after we change the absolute value bars to parentheses? And how you determine it is you plug in an appropriate number. So in this case, we are going to plug in the number 6.1-ish. So it's going to be 18 minus 3 times 6.1. Again, I don't care about what the actual number is, but 6.1 times 3 is going to be slightly bigger than 18. So this is going to be a negative number. So how do you get rid of absolute value when the quantity inside the absolute value is negative? Well, all you're going to do is change those absolute value bars to parentheses, and then you're going to put a negative in the front. So in this case, it's limit, that's 6 plus. It's going to be 18 minus 3x. So again, the absolute value bars became beautiful, beautiful parentheses. We have a negative though, because we are on a negative quantity. So notice here we have a right side thing where it's a negative quantity, and then we have x minus 6 on the bottom. Same thing as the previous one. Let's try to take out a negative 3. So it's going to be limit as x goes to 6 plus. Taking out a negative 3 will be negative 3 times x minus 6 over x minus 6. Oh, I didn't do this correctly because when you take out the negative, there's already this negative here. So this is going to be positive then. So it's negative, negative. Be careful. This is going to cancel out. So it looks like this one you'll get 3. So all of this work is we split it up into two different limits. The left limit gave us negative 3. The right limit gave us 3. So what does that mean for our actual limit itself? Because the left limit does not equal the right limit, that means that our function is going to be, does not exist for this limit. Because the left limit doesn't equal the right limit. Oftentimes when you go to what I call the split point, or the sharp point of the absolute value bars, which is going to be the quantity, the number that makes the quantity in the absolute value bar 0. And if you're going to that number, oftentimes you'll get does not exist, because you'll have this left action and this right action. But even in this hardest case, even if we're going to the limit as x goes to 6, all we do is we split it up, split the limits, take each limit separately. On each limit, you're going to be on different pieces of the absolute value bar. So for example, on this one, it was the left side that gave me the right, so that absolute value bars just appeared. And then the right side gave me a negative, so then there would be a negative in front of the quantity in front of the absolute value bars. But in both cases, we got rid of them because we hate absolute value bars. We evaluated the limit, and we showed that they're not equal, so it doesn't exist. And that's all it is. So let's do maybe one more limit question, because I think we have a sense of how to do this. Again, the goal is always to get rid of absolute value bars. And then once we do that, we can talk a little bit about derivatives. So let's erase this real quick. Erase this guy. Erase this. So, new question. New question being, let's do the limit as x goes to negative infinity, 3 plus x over 2 minus absolute value of x. So notice again, I look at this limit, I'm like, I'm doing some limits for fun, as I like to do, and I come across this limit, and I'm like, oh my gosh, there's absolute value bars. But I think in my mind, I want to get rid of those absolute value bars. So what I need to do is I need to plug in some sort of number into the absolute value bars and see if I get a negative or a positive. So in this case, I'm going to plug in, remember that when you're going to negative infinity, you're not actually approaching a number called negative infinity, you're just getting bigger and bigger negative numbers in magnitude. So for example, you have negative 50, which is a big number, then negative 100, negative 1,000, negative 10,000, negative 1,000,000, negative 1 billion. X is approaching all the way over there. Keep going further and further and farther and farther and farther. So what number am I going to plug in? I'm going to plug in negative 1,000,000. So what I do is I plug it in only into the quantity that is the absolute value bars. So the quantity in the absolute value bars is literally just x. So when I plug in negative 1,000,000 into that, notice I'll get something negative. So when I plug in a negative big number in magnitude, so negative 1,000,000, negative 1 billion, when I plug this in, I'll get a negative quantity. So how do you get rid of absolute value bars with a negative quantity? All you do is you erase the absolute value bars and you put a negative in front of that. So in this case, it'll be limit as x goes to negative infinity, 3. So I'm changing my absolute value bars to be parentheses, and then all I do is I put a negative in front here. So this was already a negative, so we can put a negative here, and then it's 2 minus. So notice that I don't put the negative at the very, very front, because the 3 wasn't originally in the absolute value bars. Same thing with this 2. I didn't put the negative in front of the 2. All I did is put it in front of the thing that was in the quantity inside the absolute value bar. So that's why the negative just went right here. Obviously, negative negative is equal to a plus. So let's change this to a nice little plus here. And notice that this is so much lovelier than this because the absolute value bars are not in this guy, but they are in this guy. So now all we have to do is evaluate this limit. There's definitely various ways to do this. Because we are going to infinity and negative infinity, we call this a same heavy, top heavy, bottom heavy limit. Check out our limits involving infinity video if you want more practice with this. But basically what happens is you look at the leading exponent of the numerator and the denominator, and you look at those terms and compare them. So in this case, we have x and x because that's bigger than 3 and 2. This is technically x to the 0, x to the 0, where this is x to the 1 and x to the 1. So we're going to ignore the 3 and the 2. We're only going to look at the x and the x. Notice that this is to the 1 and this is to the 1. So they have the same leading exponent. So this is going to be same heavy because the leading exponents are the same. Crazy, I know. So remember, how do you do same heavy questions? Well, it's just the ratio of the leading coefficients of the numerator and the denominator. Leading coefficient meaning the coefficient attached to the leading exponent, the biggest exponent. So in this case, it's going to be -1 over +1. Technically, there are 1s here. So the final answer is just -1. So even if we're going to negative infinity, as opposed to just a number, we still apply our same absolute value rules. We say, well, we are approaching a negative number, a big negative number, -1,000,000. We plug it into the quantity, into the absolute value bars. If we got something negative, which happened in this case, because the thing in the absolute value bars was just x, we just said, we know how to deal with that. All we do is change the absolute value bars to parentheses, and then we put in negative. Then to evaluate the actual limit, we did same heavy, because that's the easiest way to do limits of x go to infinity or negative infinity when it's a polynomial over polynomial. So hopefully you are armed to do all these limit questions with absolute value bars, trying to get rid of the absolute value bars. Let's talk about derivatives now. So let's go back to the original OG absolute value. So in this case, remember that absolute value looks like this V right here. So we have f of x is equal to the absolute value of x. So remember, now we want to talk about derivatives. But derivatives are just slope of the tangent line at certain points. But notice, because absolute value consists of only line segments, it's not like a parabola with a curvy guy. Well, the slope of the tangent line itself is going to be this curve. Remember that f of x is equal to, let's draw this nicely, x, the identity line for x bigger than 0, let's write absolute value actually, the negative identity line for x smaller than 0, and then you can have some sort of, wherever you want to put the equal to 0, you can put it anywhere you want here, or you can form a third portion. But this is what absolute value is. So how do you find the derivative? Well, the derivative is pretty simple. It is the slope of these lines. What is the slope of this line right here? Well, m equals 1. What is the slope of this line right here? Well, m is equal to -1. So, for example, what's the derivative? Well, the derivative of any point greater than 0 is just the slope of this line, because the tangent line to this line segment is just the line segment itself. So in this case, it's just going to be 1. The derivative of x is 1. It's one of the easiest derivatives that we have been doing because we are sort of derivative masters by now. So this is for x bigger than 0. Again, it's just the slope. What's the slope of just the x? That's going to be 1 because it's mx plus b. No plus b, m is 1. Then what's the slope of this line? Well, it's going to be this coefficient right here, which is -1 for x smaller than 0. So this derivative looks pretty simple. It's either 1 or -1. There is one problem point. The problem point is this little sucker right here, the sharp point. So I'm going to call this the sharp point. Because why is this a cumbersome thing? Well, first off, it's sharp. If you run your finger along it, ouch, it will hurt you. So just keep in mind that the sharp point is dangerous. And why is it dangerous? Well, look at the slope here. The slope is 1. Look at the slope here. The slope is -1. But they meet at this sharp point. So what should we describe the slope as? 1 or -1? Well, we can't choose two slopes for a single point. So that's why this thing actually isn't differentiable at this point. It doesn't have a derivative. So in this thing, when we list out our steps, or list out our portions of the derivative, it's going to actually does not exist for x being equal to 0. So at the sharp point, the derivative doesn't exist because it's sharp. There's two slopes here, and you can't have two slopes. So just keep in mind that when you're dealing with absolute value, especially at absolute value of lines, the other points are all going to be okay. Usually the derivatives are pretty easy. In this case, they're going to be constants. You have to worry about the things that make the absolute value equal to 0, because then you might be forming sharp points. And the sharp point is the canonical example of a function that is continuous at a point but not differentiable. So f is not continuous, is continuous, but not differentiable. At the sharp point. So in this case, it's x equals 0. Because it is continuous, notice that as I draw this picture, I don't lift up my pencil or my marker here as I draw the sharp point, but the sharp point means that the derivative doesn't exist at that point. So that's all it is. Sometimes they ask these questions in sort of theoretical multiple choice questions where all the 4 choices are sort of reasoning. But if you know this fact that the derivative of the absolute value doesn't exist at the sharp point, but it's still continuous there because you don't lift your pencil as you draw it, you should be fine as you do those questions. But let's try to take a few derivatives and then we should be good to go. So let me erase this real quick. So we have this, we have this. So my question is, let's take the derivative of f of x equals absolute value of 2x minus 6. So we're going to try to list out the derivative, and it should be easy to find derivative points. So what I'm going to do is, again, even with limits and same with limits, what we did is we broke things up. So let's try to break this function up as much as possible. The left side and the right side and maybe the sharp point. So how do you find the sharp point? It's pretty easy. Same thing with the previous questions. What you do is you set the thing in the absolute value to equal 0. X is equal to 3 in this case. So this is going to be my problem point. So just like that, the function itself, absolute value is piecewise, that's going to make the derivative piecewise as well. So in this case, because x is equal to 3 makes this 0, we're going to split it up at 3. So we have 4x smaller than 3, we have 4x bigger than 3, and then we have 4x exactly 3. So these are going to be my 3 pieces of the absolute value. The left side, the right side, or the negative side, the positive side, and then the sharp point itself. So let's try to get rid of absolute value bars just like normal. So let's try to write this function as a piecewise function, and that will allow me to take the derivative more easily. Same thing as the limits. So we have a case for x is smaller than 3. What is the function for x smaller than 3? Well, what you do, again, just like what we did before, we're going to plug in a number to the left of 3 because we're doing less than 3. So let's plug in 2.9 for example. When you plug in 2.9, 2.9 times 2 minus 6 is going to be some negative quantity. What do we deal with negative quantities? Well, all we do is we erase the absolute value bars. So we're going to change them to parentheses. And then instead we're going to put a negative here. And that's all it is. Same thing with the right side. We're going to plug in a number greater than 3. So it's going to be 4x greater than 3. Let's say 3.1. I don't care about what actually the number is. All I do is I plug it into the quantity inside the absolute value bars. 3.1 times 2 minus 6 is a positive quantity. That's great because how do you get rid of the absolute value bars? Well, the absolute value bars aren't doing anything on that side. So it's going to be 2x minus 6. Finally, for x equals to 3, that's going to be the sharp point. When you plug in 3, you'll get 0. So this is going to be the sharp point. So notice that when we know that this is the sharp point, all of the derivatives are going to be very easy because we're going to have to take derivatives just individually, piece by piece by piece. We don't have to think about absolute value all as a whole. We can just take the derivative of this nice simple function, the derivative of this nice simple function, and finally we can deal with the sharp point. Because these don't have absolute value bars, the derivatives are very easy. What's the derivative of the side for x less than 3? Well, that's just going to be minus 2. Because it's y equals mx plus b, just the slope, negative 2. The slope of the derivative of negative 2x is negative 2, just like the derivative of 7x is 7. The derivative of plus 12, or not plus 12, plus 6, when you factor out the negatives, or factor in the negatives, is just a 0 because the derivative of any constant is 0. Definitely made that much harder than it had to be. So let's take this derivative real quick. What's the derivative of 2x? Again, it's 2. What's the derivative of minus 6? That's 0, so it's going to be 2 here. And then what's the derivative at the sharp point? Well, you can't have the slope of negative 2 and 2, so the slope is just going to be, does not exist, because this is the sharp point. So if you wanted to find the derivative at certain values, well, it's very, very easy once you list out the entire function. For example, what's f prime of 0? Well, 0 is less than 3, so f prime of 0 is equal to negative 2 in this case. What's f prime of 17? Well, 17 is greater than 3, so f prime of 17 for this function right here is going to be 2. And then the problem point, the start point, the split point, whatever you want to call it, what's f prime of 3? Well, again, that doesn't exist because that's the start point. That's the point that has 2 slopes, meaning that it has no slopes. And that's all it is. Again, the same strategy as we do limits, trying to split up the function into individual pieces so that we can get rid of the absolute value bars. And then when we get rid of absolute value bars, usually the question becomes easier, whether that be a limit or a derivative. Let's do one last one. Let's erase this real quick. Let's erase this. So let's do a harder question. Let's have a function be something like the absolute value of x squared minus 9. And what we're going to do is we are going to try to write this as a derivative. We're going to try to write the derivative of this function piecewise. So again, what we need to do is we need to focus on splitting up the absolute value bars so that when we get rid of the absolute value bars, the derivatives will be quite easy. What makes this 0? Well, I can do that work on the side. X squared minus 9 is equal to 0. That means that x is equal to 3. Because you get x squared is equal to 9. So remember, when you take the square root, you do need plus or minus. So it's plus or minus 3. So we're going to have for x, we're going to have a bunch of pieces in this case. We have for x smaller than 3. That's one of the intervals. Then we'll have x from 0x to 3. Then we'll have for x bigger than 3. And then finally, we'll have the sharp points, which are again were the numbers that made the quantity inside the absolute value bar 0. So in this case, it's x is equal to negative 3 or 3. So let's try to get rid of absolute value bars. So for x is less than 3, what do we want? All of these are going to be x squared minus 9, x squared minus 9, x squared minus 9. And then this one right here, well, when you plug in 3 or negative 3, you get 0 because this is the sharp point. We can write sharp point here, or sharp points actually. So this is the sharp points. So what we need to determine is, do we want to put negatives in front of all of these? And that's basically it. So what we do again is we plug in a number bigger than that quantity, we plug in an appropriate number in the interval. If it's positive, we just leave it like this. If it's negative, we'll write a negative in front of it. So for example, let's take the x bigger than 3, because that's the easiest case. Let's choose any number bigger than 3. Let's choose 4, for example. Well, when you plug in 4 squared minus 9, I don't even care what that is. I just know it's positive. So this one is going to have a positive in here. And that's all it is. Let's take the between 0 and 3. Well, from 0 to 3, let's choose a number like 2. Well, 2 squared minus 9, that's going to be a negative quantity. So how do you get rid of absolute value bars with a negative quantity? All you do is you change the absolute value bars to parentheses and you put a negative in front. Finally, x is less than 3. That's a number like 0. This should be x less than negative 3. Oh, I really butchered this. Let's put negative 3 here. Let me remind. So I don't know why I did that, but it's negative 3, and so the split points are negative 3 and 3. So that means that the intervals we care about, we don't care about 0 because 0 is not a number that makes this 0, the quantity 0. We care about negative 3 and 3. So my first piece was x is less than negative 3. My second piece is negative 3 to 3. And then my third piece is greater than 3. Sorry about that. But it's still the same idea. We plug in appropriate numbers in the interval because the numbers that were the problem points, the sharp points, were this plus or minus 3. So what we're doing is we're just plugging in appropriate numbers to make sure is our absolute value but positive or negative. For this guy right here, we plugged in the number 4 and we got a positive thing. For this guy right here, any number between negative 3 and 3, we plugged in 2, so we got a negative thing. Finally, for x is less than negative 3, we want to plug in a number less than -3. Let's take -4. But when we plug in -4, that will square. You'll get 16. 16 minus 9, that's still a positive quantity, so it's a positive thing. So hopefully that didn't make cause too much confusion when I wrote these interval wrongs. But again, what you do is at the very beginning, find your split points. So for example, in this case, it was -3 to 3. So you want to consider everything around -3 and 3. So the first interval should have been, as it is on the board right now, x is less than -3. The next one should be -3 to 3. One split point to the next split point. Finally, the last one is x is greater than 3. For example, if you had 3 split points like A, B, and C, you would want to consider the interval 0 to A, then you would want to consider the interval A to B, B to C, and then greater than C, and then you can consider your split points or your sharp points afterwards. So because we had plus or minus 3 as our split points, we went from numbers smaller than -3, the numbers between -3 and 3, and the numbers greater than 3. This encompasses all the possible cases when dealing with these sharp points. So finally, let's take the derivative, f prime of x. Again, all we have to do is to take the derivative. It's going to be very, very easy because we've already done all the hard work. So what's the derivative of this guy right here, which is going to be 2x. For x is smaller than -3, let's have the right interval this time. So for x is smaller than -3, we have 2x. Then, right here, the derivative is going to be minus 2x. For x is in between -3 and 3. And then for this guy right here, what's the derivative of x squared minus 9? Again, all this was the power. We'll take the power in the front, drop it to the front. The derivative of minus 9 is 0. So this is going to be 2x as well. And then finally, what's the derivative at the sharp points? Well, the sharp points are sharp for a reason. They're dangerous. That means the derivatives don't exist. So 0 for x equal -3 and 3. And by 0, I mean doesn't exist. So that's that. Again, even in these harder variations, the goal from the very beginning was always the same. Try to get rid of the absolute value bars. And how you do that is you might need to split up the function into different pieces where the different pieces are broken up by the sharp points, the thing that makes the quantity equal to 0. So we did this for limits and we did this for derivatives. In this case, the sharp points were -3 and 3, so that's where we broke it up after a minute or so. Then, once you've gotten rid of the absolute value bars, it's very easy to do the question, whether it be a derivative or a limit, because there's no absolute value bars left. And in order to get rid of the absolute value bars, what you do is you plug in an appropriate number in your interval. So for example, in this case, we plugged in -4. In this case, we plugged in number 0 or 1 or 2. When we were going from x limits as x goes to 2 from the left, we would plug in something like 1.9. What you do is you plug in that number, and once you plug in that number, if you get a negative quantity, just negate your quantity. And if you get a positive thing, you can just erase the absolute value bars. And that's that. If you want more practice with this, because still absolute value is a tricky topic, be sure to watch our Girls Teach Calculus video, which I'll link in the description of this video, where one of my former students practices several of these examples. She does limit questions, she does derivative questions, and in each of the questions, she asks the question, how can I get rid of the absolute value bars? How can I get rid of these absolute value bars? And she carries about the same process that we've discussed today. But thanks again for watching for this video. Sorry about this little confusion on the last question, but hopefully you see that it was like the previous questions where we dealt with intervals and absolute value bars and trying to get rid of them as quickly as possible in the same way that we did all the other questions where we had an appropriate interval. X is less than -3 in this case, and between -3 and 3, x is greater than 3. Thanks again for watching. Just like normal, we definitely appreciate it. If this was beneficial to you at all, give us a like and subscribe to our channel. We will be dealing with absolute value later on in the course when we hit integrals, but even when we hit integrals, it'll be the same process. Try to split it up. Try to think of the absolute value as 2 different pieces. So if you continue watching this basic derivative topics playlist, or we continue watching our videos, we thank you, and we cannot thank you enough. And thank you again for watching this particular video. Hope to see you next time.